We don't want to hear.
I think it's a good idea.
All right. So if f of a equals f of b, so you have 2 points whose output is the same. So let me sketch a graph for that. So here will be my point A, and here will be my point B. And f of a's value, so let's say it's a negative y coordinate, is exactly equal to f of b's value. And this function has to be continuous and differentiable on the open interval. So if I kind of connect these in any way I want to, you guys can connect them in any way that you want to, then there exists at least one number c within that interval such that the derivative at c is 0. Well, based on my sketch, how many places does this have a derivative of 0? 3. Okay, so this guarantees at least one. Okay, kind of a couple other possibilities. I mean, there's a gazillion possibilities, but it makes sense. You have to start at the same level that you're ending at. So if you increase or decrease at all from the start, let's say increase at first, I have to turn back around if I'm differentiable and continuous. I have to turn back around. And so there is a spot in between where the slope is 0. Yes? And even if I did something like this, A and B, and my f of A and f of B were connected with a straight line, there is still at least one c value. In fact, there's an infinite number of c values in between where the slope is 0, right? So here we have an infinite number of c locations where the slope is 0, just because it's a flat horizontal line, the slope is always 0. With, kind of one increasing interval and then one decreasing interval, you get one value of c, and then you can obviously fluctuate as many times as you want. Like here I would have a c sub 1, c sub 2, c sub 3. This guy has 3 different c values, but the Rolle's theorem says you have at least one, if not an infinite number of them if you ever did a horizontal line. Okie doke? Okay. So the first example here asks us to find the 2 x-intercepts of the function. Okay, we're going to start with that. So here's a function. What are the 2 x-intercepts of this function? X-intercepts are when y equals 0, 0 and 3. So x equals 0, x equals 3. So I'm just going to sketch this, obviously. The reason Rolle's theorem is going to be applied here is because f of a and f of b are at the exact same y coordinate of 0. Okay? What happens in between is that we know that we are guaranteed that there's at least one c value in between at which the derivative is 0. And so that's what the second part of our sentence is asking us for. Show us that f prime of x equals 0 at some point between those x-intercepts. So we're going to take the derivative. Now, how do you want to take the derivative of this? I would too. I would change the original distribute. We could do the product rule if we were feeling ambitious, but just distribute, and then the derivative is just 2x minus 3. And set it equal to 0. And prove that the 0 slope is going to occur between 0 and 3 on our x-axis. So we add 3 to both sides, divide by 2. We get at 1.5 is where we're going to have it, which we all could figure out with this type of problem, I would think, because it's a quadratic. And quadratic zeros are symmetrical around the vertex, so 0 and 3 means that our vertex is at 1.5. But not all functions are like that, right? Okay, we've been doing over the past couple of years polynomial functions. So if I have something like this, like this, like this, the maximum doesn't have to happen halfway in between the 2 points. In fact, the crazier your functions get, they won't. So we have 2 zeros. This minimum does not have to be halfway in between. In fact, this one looks like it's maybe even a little bit over. Parabolas, we know that the maximum has to be halfway in between, so the 1.5 makes sense. And just to be more specific, we know that this parabola opens up or down? Up, because it's positive x squared. So something like this, your vertex is at 1.5 comma something, and it doesn't ask us to come up with what that is, but just showing that at that vertex our slope is 0, it's at 1.5. And the biggest thing is that 1.5 falls between. That's our C value that's falling between our A and B. Any questions on that? Okay, so something whose graph we're a little less familiar with. We're going to find the y-intercepts of this graph. So setting y equal to 0, what are the x-intercepts? When will that equation equal 0? 0, correct? And -1. So, roughly speaking on a graph, not really knowing at all what this type of graph looks like, we have a y-intercept at 0, and we have, an x-intercept at 0 and an x-intercept at -1. So we're trying to prove that somewhere in between there, the slope is 0. So we're going to find the derivative. How would we like to find the derivative here? Okay, so there's a rewrite. -3x times x plus 1 to the 1/2. And then what method? Product. Has to be the product. We have our first times the derivative of our second, which is 1/2, times x plus 1 to the -1/2, times the derivative of what's inside. There's a chain there. What's the derivative of what's inside? Just 1. So we don't have to, if you did forget the chain rule there, you'd get lucky to get away with it. First times derivative of the second plus the second, and what's the derivative of the first? -3. Okay, so I'm going to clean this up. We have -3x over 2 root x plus 1 plus -3 root x plus 1. And I want to know when this equals 0. Rolle's theorem tells me it should be between my two x-intercepts. So, algebraic method of solving this. What should we do first, Sam? Which one would be easier to move over to? This one? Sure. So -3x over 2 root x plus 1 equals 3 root x plus 1. Then what? Divide both sides? When you divide this by root x plus 1, that'll cancel. When you divide this by root x plus 1, I'm a little... What's that going to do? So -3x over 2, and then root x plus, this root x plus 1, when you divide it, you put it in the denominator, it becomes x plus 1 equals 3. is there, what else would somebody, I would be surprised if everyone was going to do that, Dylan? Right, most people would have multiplied this one out of the denominator, right? It's a little odd to divide away this x plus 1, root x plus 1, and get 3 out by itself. It's obviously going to work, but most people would just multiply this away, or put this over 1 and cross multiply. Okay, same thing. We'll all end up at the same spot, I think, because right now, Sam, what would you do? Given where your problem is. Okay. Keep going. Yeah, our algebra, that's our weak link here. I think that's really what the Common Core did to you, to be honest with you. It made you think a little bit deeper about certain topics, but your basic, like, solving skills and the intensity of the types of problems that you're able to solve are not as good as they used to be before the Common Core, when it was very straightforward and a lot of skills-based stuff. So that concerns me, but it's just an observation. Bryce? Right. Eventually, you have to get this out of the denominator. When you have a variable in the denominator, which is why it would have made more sense to do it up there, but eventually you have to multiply this out of there. So we would have negative x equals 2 times x plus 1. And then now it's straightforward. But if you guys have a variable in the denominator, you want to get it out. Okay? So way back here, I would cross multiply, and I would say negative 3x equals, cross multiply here, your 2 times 3 is 6, and your root x plus 1 times root x plus 1 is x plus 1. And then, now if you wanted to divide both sides by 3, it would simplify to this, but, you know, kind of just getting there a lot more painlessly. From here, we're just going to subtract our 2x over. So we have negative 3x equals 2, and divide both sides by negative 3. So it's telling us that this 0 is occurring at negative 2/3. Is that between the 0 and negative 1, the f of a and the f of b? Yes. Is it perfectly halfway in between? No, which is, you know, kind of what these non-perfect quadratics can make happen. So I'll just show you this function so we can just fully make sense of it. Negative 3x square root of x plus 1. And I'll go from negative 5 to 5. See if that's enough. Yeah. So that's what the function looks like. And obviously you're seeing that it's kind of got this parabola look to it, although it doesn't, you know, fully pan out. The fact that this is not touching the x-axis is just kind of a pixel error on the calculator's part. If I were to zoom in to the origin, I should, well, it didn't even get that much closer, but you see, obviously, that makes that happening at negative 2/3 makes sense. So now when I second trace and find my maximum, we've already found the x-coordinate at which it's located. So there's my left bound, enter. There's my right bound, enter, enter, and it's happening at negative 2/3. Okay? So really for the first time, we're able to find maximums and minimums on non-traditional parabolas. Okay? Just by setting the derivative equal to 0. All right. Next set of examples, determining whether Rolle's theorem can be applied. Okay, so that, again, the two restrictions for that are, is the interval continuous, or is the function continuous and differentiable? So looking at this first one, is this function continuous? Yes, it always is. And it's always differentiable, so the interval is not that important. So if it can, find all the values in A and B such that f prime of C is 0. So, take your derivative, 2x minus 5, set it equal to 0. Add 5 to both sides, divide by 2. Is that in the interval? Yes. Actually, there's one other thing I failed to do that I should have done. What did I forget to do that is the only way Rolle's theorem can be applied? The only way we'll know for sure that something will fall in that interval prior to actually finding it, right? Right, making sure that the y coordinates of f of 1 and f of 4 are the same. Now before, we did make sure that they were the same by just ensuring that they were, that we were dealing with an interval of 2x intercepts. Obviously those both have a y coordinate of 0. These may or may not. If I do f of 1, I do get 0. It doesn't have to be 0 though. It could be f of 1 equals 7 and f of 4 equals 7. 4 is 16 minus 20. Yep, that's 0 too. So, between that, the continuous, the differentiable, those are our 3 restrictions, ensuring us that Rolle's theorem should give us some number, at least 1, if not more. You may have a twist at you, and that would be, but you'd have to, it's kind of like factoring out a GCF. We get so used to nothing having a GCF that we forget to look for it. So if something ever came up on a multiple choice, it seems fishy, like, I feel like something's not right here, like, go back and make sure that those restrictions are applied. Alright, so, same thing here, what's f of 0? F of 6, okay, and is this function differentiable and continuous along the interval from 0 to 6? No, why not? Sharp corner point. This is an absolute value graph. Here's your parent. That's been shifted right 3 units, which puts it here. That's the x minus 3. Then the negative out in front means it's been flipped upside down. And then this additional 3 means it's been shifted up 3. So that's what it looks like. And from 0 to 6, even though they both are the x-intercepts and obviously therefore have the same y coordinate of 0, there is no point on this graph where the slope will equal 0. Right? Because it is not differentiable at x equals 3. So, Rolle's theorem cannot be applied. There you go, Owen. How was that? So you'll have to be on the lookout for discontinuities on an interval that might be caused by a piecewise function, might be caused by an asymptote, might be caused by a hole. And also situations where things are not differentiable, which would really be because of those discontinuities or because of a sharp corner point. Good. What do we have here? Oh, nice. More practice. Let's find our points first. What's the cosine of 0? What's the cosine of 2 pi? Okay, so that checks out. Is the cosine function continuous? Is it differentiable? So we should have no problem setting our derivative, which is what? Equal to 0. And we should have no problem finding at least 1 point, if not more points, on this interval. Question. What's the first solution you come up with to this? X equals 0. Now my question is, do we include that or not? Okay? Let's look at the definition a little bit more clearly, or carefully. If the function is continuous and differentiable on the closed interval. Oh no, this says open interval. I might have paraphrased that. It might say, let me just check the book real quick. It might say, yeah, Rolle's theorem actually says on the closed interval initially. No, it doesn't. I tried to condense this definition. Here's what it really says. Now this is not false, by the way. This is still true. Because what the real theorem says is that it has to be continuous on A to B and differentiable from A to B, open. Because obviously with endpoints, you can't be differentiable at the endpoint, right? So it's just saying it has to be differentiable between the endpoints. Does that make sense? But you can be continuous at the endpoint, and we need to be continuous at the endpoint. We need to have closed circles at the endpoint, otherwise the slope between the two endpoints wouldn't exist. If they were open circles, then those points wouldn't exist, so you'd never have like an average rate of change between those. So I did kind of paraphrase this a little bit, but nonetheless, we are definitely continuous from 0 to 2 pi, and we're definitely differentiable between that 0 and 2 pi. Okay? And then when it tells us that we have at least one C value, the C value has to be on the open interval. It cannot be at one of the endpoints. So given that, do we include x equals 0 as one solution? No, our solutions must be on 0 to 2 pi interval with parentheses. So we are not going to include 0. As we travel around the unit circle, where else is the sign 0? Pi. Anywhere else? No. It would be 2 pi, but we don't include the endpoints here. So it's just at x equals pi. Okay, does it say to find the point? Yeah. Oh no, find all values in A and B. So we found our value. If they wanted you to find all the points in that interval, you would then obviously have to plug in pi to find the y coordinate. And what is the cosine of pi? -1. So just pay attention to that direction. Are they just looking for the C value? If so, that's just your x value. Are they looking for the full point? If so, you have to plug those x values back in. Okie doke? Okay. Secant graph. Now this is going to require a little more thought. Secant is the same as 1 over cosine, right? We do better with that. Is this continuous is going to be my concern because we do have some undefined here. Is this continuous from negative pi over 4 to pi over 4? In other words, is there a 0 for a cosine anywhere between those two numbers? Think about your unit circle. We've got negative pi over 4 to positive pi over 4 is where we're looking. Is there any place in there where the cosine is going to be 0, which would give us a 1 over 0? No. So we are luckily continuous. If you remember the secant curve, it is differentiable everywhere except for at its discontinuities. But again, our discontinuities are not happening in this interval, so it is also differentiable within that interval. And then we got to plug in our points. We got negative pi over 4. If we plug in negative pi over 4, and I'm going to plug it in here, what's the cosine of negative pi over 4? Positive, because it's a fourth quadrant angle. Negative pi over 4 is in the fourth quadrant, and cosine of that should still be positive, right? So it's 1 over root 2 over 2, which is just the reciprocal of root 2 over 2. And then when we plug in positive pi over 4, obviously cosine's also going to be positive. Cosine of pi over 4 is root 2 over 2. So 1 over root 2 over 2 again reciprocates it. So we've got those y coordinates the same. Yep. If you're just kind of showing that it's, when you rationalize, if they're the same prior to rationalization, they're obviously going to be the same after. So if you're just using it to determine whether or not it's not like that's an answer of any sort. So I would say don't bother. So now we have to find out where. So what is the derivative of secant? Secant x tan x. And we want to know where this equals 0 on this interval. Okay, so between negative pi over 4 to positive pi over 4. So either, we could tee it up right now, either the secant x equals 0 or the tangent of x equals 0. And guess what? Which one of those never equals 0? Secant, because 1 over anything would never equal 0. And in this interval, when is the tangent equal to 0? Just at 0. Okay? The tangent of 0 is 0. So x equals 0 would be your C value here. If they ever wanted the point, again, we would plug back in 0 to the original. What is the secant of 0? In other words, what is 1 over the cosine of 0? 1. Let's kind of shed some light on this via 1 over the cosine of x. I'm going to do my interval from negative pi over 4 to positive pi over 4. I'm going to count by, I don't know, pi over 4. We'll do pi over 8 just for fun. Negative 5 to 5. So there's my secant graph just in that small interval. Now that obviously looks a little bit different to you guys because we're not used to looking at such a restricted interval. We're used to looking at like negative 2 pi to positive 2 pi, so we get several periods and full cycles of this in. But if that's your secant graph, you can kind of confirm that at the bottom it's hitting a minimum, right? At the start of the interval and at the end of the interval, they're at the same level. So it's decreasing at first, so at some point it must turn around and start increasing back to its starting value, and you get a slope of 0 at 0, 1. You could trace that, see that it's 0, 1. I'm just going to do this, negative 2 pi to 2 pi, just so, as a reminder, we see what our overall secant graph looks like. But we were so narrowed in right here just a moment ago that that's all we were seeing. Okie doke? So if they ever had the secant function on the interval from, negative 2 pi to 2 pi, we'd have a lot of problems doing the Rolle's theorem there because we wouldn't, you really wouldn't be able to apply it. I mean, yes, there are still moments when the slope is 0, but there's fewer than we would think because obviously we've got a lot of discontinuities. So they specifically limited this to an interval in which you would have continuity and differentiability. Good? It's easy enough? We're not done. Just an application. Ordering and transportation cost. They give us a formula where C is measured in thousands of dollars and X is the order size in 100. Verify that C of 3 equals C of 6. So the cost for ordering 300 items supposedly is the same as the cost for ordering 600 items. Not the cost of the product, the cost of the shipping, right? The ordering and transportation cost. So if we check C of 3, you 10 times 1/3 plus 3 over 6, which is 10 times 3/6 plus 2/6 is 5/6. I got a common denominator there, we follow? C of 6. 10 times 1 over 6 plus 6 over 9. That's going to be 3/18 plus 12/18, which is 15/18. Can I reduce my 10 and 18 to 5 and 9? Reduce my 15 and my 9 by 3, so I get 5 over 3. So I get 25 over 3, which is what this would have reduced to as well. Okay, and then find the order size for which the rate of change of the cost must be 0. So C prime of X equals. What are we going to do here for our derivative? What method do we want to tackle this with? What did you say? We could distribute the 10, or we could just tackle it with the product rule, so we could just do the first times the derivative of the second, and then the second times the derivative of the first would just be a non-issue because the derivative of the first is 0. You know what I'm saying there? That actually might be easier than distributing. You could just get a common denominator, because right now, as it sits, we're going to have multiple quotient rules within there, which isn't very pretty. So you could get a common denominator. I think I might do that. Get this one with an X plus 3. And get this one with an X. And then I'd have 10 times X plus 3 plus X squared. All over X times X plus 3. And then I think I would do my first times the derivative of the second. And the derivative of the second would require the quotient rule. So I have my bottom times the derivative of the top, 2x plus 1, minus our top, times the derivative of the bottom, 2x plus 3, all over bottom squared. Not the prettiest thing I've ever done, but we're going to work with it. I'm just distributing out. Distribute out my first binomials, minus, I'm going to distribute out these. Oof. So I have 2x cubed minus 2x cubed, that's nice. I've got 7x squared minus 3, actually minus 5. So 7 of these minus 5 of these is just 2x squared. I've got a 3x minus 9x. And then minus 9. Hold on one second. If I'm setting this equal to 0, what's the only thing that needs to equal 0? The numerator, and then you'd get your answers. Okay? So your homework is there at the bottom. Quiz on Wednesday. Goodbye.